Iman Fayyad is a designer and assistant professor of architecture at the Harvard University Graduate School of Design. There she teaches and conducts research in spatial geometry with a focus on tectonics, construction, and representation. She's also the founding director of Projective, an award-winning research practice that explores architectural geometry relationship with material economy, sensory perception, and the politics of physical space and building practice. Her writing and design work have been published and exhibited in venues including the New York Times, Technology, Architecture and Design, Nexus Network Journal, Log, Teaching, Archinet, the IA Architecture Gallery, Carnegie Museum of Art, Citigroup NY, and the Rocca Gallery in London. Her public work and research on zero-based geometric construction techniques have been funded by grants through the MetLife Foundation and the Lander Center for Social Justice. And she has received recognition by the Architects newspaper, Best of Design Young Architects Prize, the ACSA Faculty Design Award, and Architect's Design for Good Award. She is also the 2024 McDowell Fellow. Previously, she was assistant professor at Syracuse University, where she coordinated the first-year design studio and taught courses in digital media. Her course on projective systems and architectural forms, designed for the new directed research program, was the recipient of the 2024 Creighton Memorial Collaborative Research Prize. Fayyad served on the faculty of MIT, Princeton, and Harvard, where she was also the inaugural John Irving Innovation Fellow. She was twice named the Architecture Faculty of the Year at Harvard University. She holds a Bachelor of Science in Architecture from MIT, not surprisingly, Phi Beta Kappa Academic Honors, and a Master in Architecture with Distinction from the Harvard Graduate School of Design, where she was a recipient of AIA Certificate of Merit, the Faculty Design Award, and the Arado Akushita Prize for Design Excellence. Prior to starting her own practice, she worked at offices in Boston and New York and Paris. So without further ado, the floor is yours. Iman, please welcome her.
Thank you so much, Toya. Can you guys hear me okay? If I project and yell. I did send you guys a very short bio, by the way, but I guess I didn't use it. Thank you so much. That was very generous, and thank you so much for inviting me to be here. My first visit to Penn State. It's really wonderful. So I'm going to show some of my work today, and I would love to leave some time for some questions at the end. I titled my talk Transient Form because I'm very interested in this sort of idea of in-betweenness or peripheral space. And I often sort of see the world through the work that I do as always sort of in this space of flux. Much of my work interrogates the discipline of projective geometry, which is, or projection more broadly, which is a practice that's all about sort of drawing parallels and drawing relationships between things, reading into relationships between things that exist in different forms in different spaces. And this way of thinking for me is predicated on the assumption that there are no absolutes in the universe. Everything is a mere instantiation of something else frozen in time. And for me, this space of projection between things is so important, it's so potent. It has us sort of thinking in multiplicities and in pluralities, less so in singularities. And I'm reminded often of the artist Agnes Dennis's philosophy that visualize humanity's achievements, paradoxes, and follies. She describes her art as existing in a dynamic evolutionary world of rapidly changing concepts and measures, where the appearances of things, facts, and events are assumed manifestations of reality, and distortions are the norm. I love these drawings of hers that are both super precise and calibrated, but also kind of funny. And for me, this dialogue between the norm and the transformed is most powerfully embodied in formal and spatial expressions that are static, but either appear to be in motion themselves or otherwise activate bodies and space around them keeping them indeterminate in perpetuity, or in other words, what I refer to as a sort of transient form. So today I'm going to talk about how I look at this phenomenon through a particular relationship in architectural practice, and that is between three-dimensional form and flatness, specifically through the lens of projection. Projection allows us to understand the linguistic conventions of architecture, how we communicate, what tools and media we use to express our ideas. The philosopher Nelson Goodman makes a distinction between two types of art, what he calls autographic and allographic, or one-stage and two-stage arts. So autographic art is something like painting, sort of a photograph, a drawing drawn by hand. It's a one-stage art. The piece of art itself is the end product. Allographic art is a notational art or an instructional art, something like music, where the notation is the piece of art that's created by the composer, but there could be infinite end products, each of which is considered an authentic production of the art. So architecture sort of is similar in this way, although I argue it's more a multi-stage than a two-stage art. But unlike music, architecture actually has, it leaves very little room for interpretation. The conventions of drawing, for instance, in the translation from drawing to building, leaves very little room for error in the translation from drawing to building. It's very different from music. Music is about the sort of like the celebration of the performer, and then the end performance becomes a piece of art in and of itself. So I'm kind of interested in the conventions of architecture and how we sort of see that as our language. Usually in the practice of architecture, it's a good thing to limit interpretation because it means that the translation from drawing to building can be more straightforward. But the questions that I like to ask are, what if you were to create room for a kind of deliberate misinterpretation as a way to challenge both the conventions that have been constrained by the limitations of our design mediums, both historically and in contemporary practice? I like to look at this drawing. This is a redrawn image of the art historian Ernst Gombrich's Gates and Grills that basically shows that there exist infinite three-dimensional realities that project into the same two-dimensional Cartesian grid. So it's sort of about visualizing the space of projection between the two-dimensional flat plane and the three-dimensional reality that it might describe. So in my research and practice and teaching, I look into how projective qualities play a role in this idea of translation and interpretation. And I explore these interests particularly through the relationship between form and flatness. It's a translation that has been hugely consequential in defining the spatial paradigms that have determined the way we occupy space, from our buildings to our city street grids. For me, flatness manifests in two ways. On the one hand, flatness as the drawing board or the picture plane onto which our image of the world is projected. What we see on the left. Historically, the drawing board has been used as a space to measure form, and then the other above to imagine it, see it. And then the second form of flatness is material flatness as a necessity for construction. I'm interested in the extent to which convention can be challenged in both those avenues. So on the one hand, I interrogate techniques of projective representation that are instrumental in discovering and inventing new forms and formal relationships, whether these relate to the experience of space or constructability. Now, on the other hand, my work engages methodologies that engage design, equate design with constructability through material flatness. So I'm interested in both this sort of visual space that relates to the kind of visual perception or cognitive understanding of space, and then the material sort of transformation from flat to form. Before I get into some of my own examples, I want to briefly touch on the lineage of architecture's history with three-dimensional form and its production through the medium of flatness, if I can refer to it as a medium, to contextualize the motivations of my interests in that medium today. As we all know, the role of flatness in the practice of architecture is a perennial problem. The drawing board and picture plane have both been responsible for the typologies and orders of the canon for centuries. Perpendicularity and symmetry of classicism due to orthography. As we all know, the image on the left, symmetry of classical orders and buildings, in this case, drawing half and sometimes maybe even just a quarter of the building to describe it in its entirety. There's a sort of efficiency in the relationship between orthographic drawing and then the three-dimensional spatial types that emerge from it. The axiality of the Renaissance due to perspectivism. And then even more recently, the tall office building, a result of labor efficiency by drawing a single orthographic plan that can be endlessly duplicated, almost endlessly. This building on the right is sort of became famous for having a very tiny, for those of you who've worked in offices before, construction document sets are like super thick documents of thousands and thousands of pages. This building had, I think, a total of like 65 drawings in the drawing set. A single typical plan is drawn, a single detail is drawn, and then it's duplicated. And so we can sort of maybe even understand the sort of the stacked tall office building as a result of obviously many other types of technological advancements in material, but also sort of largely due to the practice of the relationship between labor of design and construction. But even prior to the development of drawing as a necessary means to design and build, we see evidence of projective transformations from two-dimensional flat geometric patterning in the development of Makarna's faults, for instance. This is a type of both ornamental and structural sort of vaulting system or pendentive system that is very present in Islamic architecture. The idea behind this is these are two-dimensional geometric tessellations that are essentially define almost the entirety of the idea of this three-dimensional form. So the entire thing is sort of designed in 2D projectively, and then reconciled with the idea of a domed section. So the two-dimensional tessellation is sort of then kind of incrementally extrapolated into three-dimensional space, but really only using this two-dimensional tiling pattern. For centuries, indigenous nomadic populations had been deploying certain types of non-planar curvilinear forms, like the one we see on screen now, precisely because of their relationship with material flatness. So not with drawing in this case. In the case of the teepee of the Native American Sioux tribe, which is the one we see here, conic surfaces served optimal for the nomadic way of life because of their ability to be designed and sewn perfectly flat, and their structure made of native linear wood elements that are readily available, found. The property also made them easy to mount and dismount, and they were lightweight for transporting, so there was a super kind of efficient, useful relationship between the translation from the material flatness to the three-dimensional structure. There's actually a very specific relationship here, which will come in handy a little bit later on in my talk. But most of these teepees, and they are very unique to each tribe, but in this case, you'll notice this is the unrolled membrane of the teepee. It's a perfect semicircle, so it requires no angular calibration. It just needs a sort of measurement of length. It can be designed and sewn perfectly flat without really understanding or measuring things in three-dimensional space. But it translates into a very calibrated three-dimensional geometry that is a right circular cone. I think this is maybe a 60-degree cone. This one in particular is an oblique cone, so the apex is shifted a little bit over to the left. And what that does is it sort of clears out the space in the middle so that it's better for inhabitation, creates a larger sort of living space. The hearth is here, so it also allows for the diffusion of smoke in a little bit of, in a more efficient way. But it sort of means that there's this kind of like immediate translation between the two-dimensional flat template of it and then a highly calibrated three-dimensional form. But there's almost no need to ever really design it in 3D. You just design it entirely in 2D. Centuries later, we see similar types of forms, conic surfaces, also known as developable surfaces, or they're sort of a subset of developable surfaces and other singly ruled geometries, which are types of geometries that basically can unroll to a flat plane without any kind of distortion. I saw some of this work in the first year studio today, one of the first year studio today, so some of you guys are very familiar with this. But there's a really efficient relationship between, in this case, linear elements, whether they're drawn lines with a ruler or the ability to be able to describe these three-dimensional forms perfectly and isometrically onto a flat plane. It also meant that, and this is sort of different from the TP. TP is a very surface kind of oriented operation. This is, these drawings here are from 17th century stereotomic descriptions of the carving conic surfaces. So again, because of the sort of presence of straight ruling lines, it also means that they could be carved out of stone parts with very simple linear carving tools. So there's even though this is a sort of more of a volumetric kind of operation, there's an equally useful relationship here that translates from the mathematical property of these kinds of surfaces and the relationship with construction and drawing. Other types of curvilinear surfaces, again, centuries after that, this is sort of departing into a slightly different world, were acknowledged for their structural capacity and ability to be constructed out of linear members. So I'm sure some of you guys are very familiar with this. The thin shell doubly ruled concrete structures of the Spanish-Mexican architect Felix Candela. So different kind of property here with the ruled surfaces and the straight line, operating primarily in its structural capacity, less so for its ability to be mapped into lines. So the digital era relieved architecture of the strictures of this type of flatness to a great degree, both in terms of design and fabrication. And this has had consequences on our use of geometric norms. So in my work, I speculate on the sort of asymptotic relationship between technology and architectural innovation by questioning the limitations of the tools at our disposal today. Today, we can output any object of our imagination without truly understanding it or even authoring it. It's very easy to model something digitally, 3D, in Rhino without really understanding its measurements, its dimensions, and output it very quickly by pressing a button that 3D prints it. And what that does is it sort of removes us a little bit from the material realities, the understanding of the part to whole. How would you sort of then break that up into individual tectonic parts and understand it not just as a sort of cladding operation and one where the individual part may not necessarily have much to do with the geometry of the overall whole. And most important to me, I think, is thinking about how those kinds of relationships contribute to spatial organization. So as these issues relate to form, organization, and fabrication, we can make an overall intellectual narrative that historically there's been an inversion on two fronts in the process of design. One is in the process of design itself, which used to go from 2D, used to draw, and then it went to 3D. Now it goes from 3D, we usually start modeling something in 3D, and then goes to 2D, we draw it, and then it goes back out into 3D space. So there's sort of this additional process now that kind of, on the one hand, relieves the pressure or relationship between drawing in particular and three-dimensional form. And then it also creates a little bit more room for loss of information and translation. And then the second inversion is whereas a previous practice was sort of preoccupied with the coherent whole, these stone vaults are all perfectly symmetrical, but not every individual part, but many parts are sort of idiosyncratic in order to preserve the kind of coherence of the whole. That today we are sort of more used to seeing one-off idiosyncratic wholes as buildings and then rationalize self-similar parts. So the questions that I seek out that are sparked by this inversion is, can we, through geometric literacy, understanding these kinds of properties of surfaces like the ones I just described, develop techniques to design the part and whole simultaneously through properties that relate to material and pictorial flatness? And more importantly, can these methodologies invent new languages of architecture and expand the reach of certain types of forms and construction techniques beyond exclusive social and political domains? So I approach these techniques of geometry through three branches: projective, descriptive, and analytical. The historian Robin Evans describes projective geometry as the optical geometry, or the geometry of light. basically it is the space where objects are related to each other based on whether or not they look the same from a certain point of view. So a rectangle is related projectively to a square because it is viewed obliquely. An ellipse is a circle viewed obliquely. Those are projectively related. That's a space of projective geometry. Descriptive geometry is a discourse in and of itself. It's discourse developed in the 17th century in order to describe in two-dimensional space exclusively three-dimensional form. So prior to our digital tools, this was kind of the only way to be able to draw plan, section, and axon or an isometric. So to represent something three-dimensionally in two-dimensional space. And then lastly, analytical geometry, what I sort of describe as the invisible stuff. It's the kind of algebraic stuff, it's the calculus, it's the stuff that is embedded in the computer. But I sort of bounce around between these three geometries, and I sort of see them as three languages that try to tell the same story. Some of them are more useful and expedient for certain operations than others. So we see here, for instance, two nearly identical geometries, a tangent developable on the left, produced via descriptive method. I'm kind of using these terms loosely now, actually. On the right, the analytical method. So this is sort of produced entirely through the graphing of parametric equations relative to one another. And you can see that with one of them, the tectonic of the structure is emphasized more so than the surface, for instance. So they kind of produce different readings or different renderings of similar types of geometries. So I'm going to show a few examples of how I work in these disciplines that allow me to understand space and think architecturally. I sort of see, they're sort of my lens through which I kind of understand the discipline of architecture. My inquiries fall into three categories that are by no means mutually exclusive, and I sort of will bounce around between three of them, but I'll show a project in each one of these categories today. So the first one is perceptual. It's visual, it's cognitive, and it's a space that deals with the understanding of the subjective experience of space, the immediacy of form, three-dimensional form in affecting movement and sensory perception. The second is the isomorphic transformation of objects from flat to form. Isomorphic basically just meaning the transformation of something from 2D to 3D without a loss of information. And this work that I do here is primarily concerned with reality and tectonics. And third is spatial organization through ideas of repetition, aggregation, and continuity. So I'll start first with a research example that illustrates how pictorial space can be used to motivate formal language through movement and experience. Can you guys hear me okay?
Yes.
Fine, okay. So this is a technique I actually started developing as a thesis student in graduate school, which addresses the cognitive and bodily disconnect between the objective reality and the subjective perception of it through the use of a very specific type of perspective construction that maps three-dimensional spherical space onto two-dimensional Cartesian space. Instead of giving in to the inevitable distortion of an object on the picture plane by virtue of the subjective position of the eye. So for those of you who I think likely first year have already learned about perspective and central projection and things like this. Every projection is subjective, by the way, like even orthographic drawings are projective, parallel projection is subjective. But perspectival or central projection is entirely dependent on the relationship between the position of the eye relative to an object and then the picture plane that is in between that. So the image that's projected that we see, our image of the world, is entirely dependent on our movement through it. And what I'm trying to look at in this, through this exploration is, instead of giving into that sort of inevitable distortion on the picture plane, how can we design this projection specifically so that it can accommodate the movement of the subject relative to it? So is there a way for us to kind of think about the image of the world as the thing that allows us to kind of design and determine three-dimensional form rather than the other way around, rather than have it be purely resultant? So I look at this through a perspectival technique known as stereographic projection. Stereographic projection is also belongs to a mathematical branch of mathematics known as the principle of inversion. And it was originally invented by cartographers to map the globe onto a plane. It's a type of conformal map. What conformal maps do here on the right is essentially try to flatten the sphere or the globe, the Earth, onto a plane and preserve at least one variable in the process of transformation. I'm sure you guys are very familiar with this, but unlike the cone or the cylinder that I described earlier, spheres don't have an isometric relationship with the flat plane. They have a complicated relationship with flatness, and so they can't really unroll. In the process of unrolling them, there has to be a sort of loss of information, or there has to be a preference for preserving a certain kind of image or relationship between the things that are represented on the surface of the sphere, and then how they are represented both in terms of their relationship with each other on the surface, but also the kind of edge, like where do you even draw the seam? So what conformal maps do is there's hundreds of different types of projections of conformal maps, but basically what they do is each of them is unrolled in a certain way that preserves or makes sort of primary, at least one variable that's useful for something. So some of them, projections are more useful for navigation because you can plot straight line courses on them. Some of them are show more accurate representations of relative sizes of landmass and things like this. So, but every single one of them is kind of useful for one primary thing. And then other things are distorted relative to each other. This is the map that we are most used to seeing, the Mercator. But you see here the distortion of the ellipse up near the poles, the diminishing of the circle, getting smaller at the equator. This is what is known as the Tissot indicatrix. It's named after a French cartographer, Nicolas Tissot. But it basically indicates the degree of distortion in the transformation from the sphere to the flat plane. So the more eccentric the ellipse, the more stretched it is, the more distorted it is relative to the original sphere. So stereographic projection, which is the technique that I'm using here, is a type of conformal map that preserves, the variable that it preserves is the orthogonality between the isocurves, or the curves, the UV curve field on the surface of the sphere, in the process of projecting it into a flat plane. So if you were to take the mathematical curves that define the sphere in three-dimensional space and project it on a flat plane, the intersection, the relationship between them is preserved, and perpendicularity is preserved. So basically what that means is that it flattens the globe onto a plane when viewed from a certain point of view. There's an invisible iPhone light up here at the pole of the sphere that is sort of clipped. But if you were to replace that light of the iPhone with your eye, essentially what you see is a sphere visually flattened onto a plane. It's an imaginary and ethereal plane. It's something that doesn't exist. It only exists in your mind, and it only exists from that one particular point of view. So on the one hand, it sort of creates this duality between spherical coordinate systems, the radial, and then the rectilinear, Cartesian. On the one hand, so it sort of tries to relate two spatial types relative to one another. It creates this kind of duality of the objective object, the thing in reality, and then the one that we perceive, an imaginary one. And when used as a perspectival device, so if we use it not as a way to map the globe onto a sphere, but instead as a tool for revision, we can assign one type to physical space or Euclidean space, and then the other to visual space or spherical. So we see here this animation represents that process. The green plane or the green surface here is what you see, what you perceive the blue sphere to be. This is the location of the eye. The green surface is what you perceive, is the perceived geometry of the blue sphere as you move around it. And then this here jumping into that sphere. So this is a viewpoint from that point of view where all the red lines are converging. You can see up top that green plane sort of distorting, flattening here into a perfect square Cartesian grid. And then as you move around the sphere, it begins to sort of morph into something else. you see that it's not actually flat, but because of the way that we kind of anticipate seeing griddedness or Cartesian rectilinearity, perpendicularity, we kind of associate it with this idea of flatness. That thing that we're seeing at the top is not actually flat. It's spherical, but it looks flat. And so there's this kind of slight disconnect between what your mind kind of wants to believe that this is and the way that it exists in three-dimensional space. You'll notice that these forms are reminiscent of the morphologist Darcy Thompson's Mobius transformations. Darcy Thompson was a morphologist who basically tried to describe all species of fish as distortions of one type of fish instead of describing each of these as their own species. So you see the grid here in the background basically represents the degree of distortion that represents, how far away it is from one type of fish. I showed these, it's actually partly coincidental that it sort of looks like the Mobius transformation, but it brings up issues of what's considered to be the norm and the distorted because of our familiarity with the Cartesian grid. So I'm kind of reminded of the Agnes Dennis projections. Beyond pictorial space, what this essentially does is create objects of two identities. One that exists objectively and the other is purely perceived. It exists temporarily and only in the mind. I'm interested in fusing those two realities, essentially creating three-dimensional versions of this image. Who sees a duck here? Sees a rabbit? Sees both. Okay. This is an effect called multi-stable perception in Gestalt psychology, where you're able to kind of toggle back and forth between two images of usually opposing visual traits. This is just like two images that are completely different fused into one. And I'm really interested in this, thinking about this as a kind of three-dimensional, like the analogy of this in three-dimensional space. Are we able to kind of see two identities of something or have something exist, like a building accommodated to urban context, but also maybe do something else that is like more, has more of an allegiance to the internal workings of the building or something. But I'm kind of interested in essentially creating three-dimensional versions of this rabbit-duck illusion. The difference is that with the objects I'm showing here, it's less about this sort of Gestalt switch, like a kind of rapid switch, a binary, but more so a gradual and temporal transformation from one type to another. This here is an image. So I use this technique basically to design, speculate on the design of a concert hall in a fabricated urban context. This building is not actually moving, but because it's defined entirely with spherical and conical geometries, as you move through space, and once you stop at these sort of urban thresholds, like an intersection or something like that, the building appears to liquefy or it appears to morph, and really all it's doing is it's kind of snapping into that Cartesian grid and mirroring the context of the urban fabric at those particular points of view. So in the context of buildings, we can speculate on how both sides of the building's envelope, for example, can be activated to conform to the urban context, while accommodating the visual and experiential cues of its occupants internally. And I look at into both the kind of ideological and the spatial consequences of working in this way. Of many inversions, one is a topological one or a geometric one. Objects are sort of turned inside out. Curvilinear becomes planar, concave becomes convex, etc. And this becomes instrumental in activating perceptual misalignments between the mind and the body. But most instrumental to me really is architectural inversion. So how we can think about these kinds of techniques is not things that are just sort of smoke and mirrors. It's not just like a visual or optical kind of illusion or technique, but how can it begin to affect either like programmatic type or conventions of occupying space and things like this. So what I tried to do in this example is apply it to theater as a case study, type of building that has a long history of the power of the privileged point of view, and then try to see how we can redefine entirely how a theater can function, inverting front of house and back of house, for instance, creating new and unfamiliar relationships between audience and performer. And all of this is kind of done through the simple act of constructing the geometry of the auditorium so that every audience member can experience the privileged point. So basically, the auditorium and the seating is all designed around how the audience member enters the theater and views the entire auditorium. And because of that constraint, what happens is that the locations where the audience members enter, instead of through vomitoria around the periphery of the theater, they actually enter in the center by the stage, and then they get a view of the theater. It flattens into this sort of shoebox-like hall. And then when they turn around and walk back up to their seats, it is sort of transformed into this spherical sort of surround hall. So we see here, these are images of the facade also sort of snapping into these, the Cartesian geometry. So since then, I've continued to ruminate over these questions through writing and further explorations. I've become really interested in this, this consequence, the indicatrix of distortion, and what we sort of understand to be the norm versus the distorted, to challenge our perceptions of normative conditions. So what we typically would maybe assume to be distortions, like can those become the norm? These studies have prompted ideas about how to use static drawing or optics engagement with light to convey movement. So, you know, we think of drawing as always a kind of static medium. It's limited in the way that we sort of are able to represent the kinds of things that I just showed. Like I have to resort to animations because it's the only way to kind of define that. So it's made me sort of think about other mediums or modes of representation that can maybe play around a little bit with that kind of conventional mode of representation. So models and light sort of representing the way that we might see, for instance. As we all know, there's a long history of attempts at representing multiple projections in a single flat plane for technical and symbolic reasons that are inherently paradoxical. We see this in orthographic perspective, which is kind of an oxymoron, but orthographic perspective in Chinese scroll painting and Islamic murals. We saw it in Cubism and multi-point perspective, as well as the problem of movement and vision, placing emphasis on the singular privileged point of view. Actually is sidetracked, but this is I don't know if you guys are familiar with this. This was a technique that became known as razzle dazzle. The British Navy hired an artist to paint their warships with zebra stripes so that the movement and speed and direction of warships and their geometry also was difficult to discern by the enemy. The Germans figured it out very quickly, so it was a very short-lived technique. But it sort of brings into question this idea of like the movement of the object and the subject relative to the way that you might perceive it. So I'm currently looking at how this sort of privileged point of view can also be dispersed, so we can think a little bit more about less the static object and more so the moving subject. This animation here, for example, shows things fading in and out of coherence as you move away from that one single privileged point of view. So again, it's less about that sort of binary multi-stable thing. It's like this in-between space where multiple things can seem distorted, but then something might kind of snap into coherence at a certain point of view. So we can speculate on how these techniques can invent other types of non-spherical geometries, conflate the two divergent branches of parallel and perspective projection into a single construct. And historically, those have been sort of considered as separate things, fusing the indexical with the subjective as well. So I've been kind of interested, this is just a quick study, but starting to think a little bit more also beyond just visuality or vision as the kind of what Ponti described as the mother of all senses. Like how can we sort of think about cognitive perception or bodily movement and experience as something that is not only explicitly dictated by vision, but other forms of bodily awareness. So I've been looking at other ways. Again, these are slightly less precise. They deal less specifically with a certain technique, but begin to look at how perceptions of certain geometries that maybe don't want to be together, like a sphere, a closed volume, very hermetic, that's kind of being ripped apart into a surface that's unfurling. And they're kind of just studies in sort of like, these are small little 3D printed models. So holding them a certain way or seeing them in different views, kind of understanding how volume and surface begin to work with one another. Okay. So with an interest in fusing my investigations in pictorial ambiguity with material and tectonic ideas, this series of drawings here sort of is like a hinge between the work that I just showed and some of my more materially focused studies. They borrow from two disparate developments in the role of the image in architectural thought over history. On the left is a type of descriptive drawing developed in the 17th century during the practice of stereotomy, the art and science of cutting stone, known as a trait. It's a type of drawing that basically became sort of like a cut sheet of sorts. It's a type of drawing that contains all of the information that a stonemason needs to construct the stone arch. So it always included a plan, a section, and then an unrolled plan or section, and then an axon or isometric of the object. You'll notice that there's no line weight differentiation here in this drawing. It's super descriptive, but the projectors are also kind of competing on the page for attention with the description of the arch. So kind of emphasizing the process over the product. At some point, somebody said that it was sort of trying to make a statement about how the intellectual difficulty of constructing this drawing surpassed the physical difficulty of carving stone. So it's supposed to kind of deliberately look complicated. And then on the right, we see a totally different kind of, borrowing from a totally different kind of practice. This is a woodcut by Joseph Albers in the work that he started developing, known as op art or optical art, kind of like these optical illusions, but it is very minimal. The historian describes this as producing maximum effect with minimal means. So how can you sort of produce a multiplicity of images or imaginations or readings of three-dimensional form with as few lines as possible? Actually, the power of an image like this to be able to see so many different types of things, kind of like the rabbit and the duck, is only possible because of the few lines that exist. It's kind of the opposite of what this is doing here. So I tried to kind of think about how we can work with these two together. I'm kind of interested in the pictorial ambiguity, but then also think about what that means when you do try to recreate these images. I always used to try to see, like, you know, kind of MC Escher, like I've always looked at Albers's drawings and wanted to make these things and see if they could exist, or like how many different versions of this I could produce. And so I was really interested in this translation from something that is pictorial or cognitive, and then its material reality. And so what this series of drawings does is essentially produce, it's drawn in diptychs, but essentially it uses the sort of gestalt techniques of multi-stable perception, similar to what Albers uses, using geometries deliberately that have an immediate relationship with flatness. So these are all geometries that are developable, cones and cylinders, super simple geometries that can be drawn without the use of a 3D model. These are drawings made not as like Make-2Ds, but they could just be made out of circles, ellipses, or straight lines. And the idea is that because these are types of geometries that can unroll perfectly flat, you can kind of create a cut sheet or an unrolled surface of it manually by developing the sort of interpreted surface, and then create a super descriptive drawing that basically allows you to turn the drawing into a model. So if this here is the unrolled surface kind of superimposed onto the perceptual image, these images, like the perceived image here, is basically kind of plays with that idea of multi-stable perception. So you see concave and convex sort of like meeting each other, or surfaces that kind of stitch in both parallel and perpendicular planes simultaneously. The object sort of flips inside out. It looks like it's self-intersecting. But because it's able to be unrolled, you can necessarily produce a three-dimensional model out of it. The only problem is that none of these physical models will ever produce the image that you're trying to see, because it's not a real image, it's a fictional reality. But it produces an object that is real in its own right, it just has its own identity. And so I am just kind of interested in this sort of like, you know, what is something that can be perceived purely in the mind? Like, what are the kind of multiplicities or pluralities that can be created from it? I use this drawing as drawing exercise now as a exercise I do with my students, typically first-year students. basically in talking about, on the one hand, the ambiguity of two-dimensional drawing and the fact that, two-dimensional drawing isn't so absolute. We think it is, so sort of thinking back to what I was saying in the very beginning about how we can challenge the conventions of our notation systems. How can we sort of look at drawings as things that are kind of infinitely malleable? What it also does is it kind of introduces students very quickly to the relationship between visually perceiving something or creating an image up in your mind of something, and then the haptic understanding of how material wants to behave. And oftentimes they're kind of in conflict with one another. So these types of geometries want to bend a certain way because of the way that they're cut, but your mind is trying to get them to do something else. And there's that kind of conflict between the haptic and the perceived that I'm really interested in. So building off of that, I want to show an example of a research project that looks into how material flatness itself can be linked to drawing in a similar way. So I'm looking here at techniques that produce design and constructability simultaneously. In other words, trying to link the process of design and construction into a more seamless relationship. And it also allows us to think about material economy and labor early in the design process rather than as something that it kind of happens at the end. And I'm looking at these in particular right now through developable geometries because of that isometric relationship with flatness. Again, just cones and cylinders, very simple geometries. And for me, these are very useful because they operate at they're very scalable. So they operate at the scale of the detail. It can also operate at the scale of the massing. And I'll show examples that deal with basically both of those things. I'm going to maybe focus a little bit on this specific idea here, that of the highly calibrated relationship between drawing and form and materiality. When I say materiality here, I'm referring specifically to the quality of the materials, their sources and their dimensions and their behaviors. Earlier, I showed a trait of the stone arch. One of the more well-known examples of stereotomic form is the trompe or the squinch. This is a conical surface that was used historically to stitch concave 90-degree planar corners with each other. And its origins rest in the attempt to reconcile between an orthogonal plan of a transept and the circular base of a dome. So it kind of was an attempt at a solution to produce the pendentive. The pendentive is that patch of surface that tries to reconcile circular base of a dome with what typically was either a square base of the transept, sometimes octagonal. The cone was a sort of kind of natural way to do that because it has in it inherently both straight lines and circles, so it's able to kind of stitch seamlessly between them. I like looking at these images here. These are developed around the same time, actually, in the 10th century in Eastern Europe. But you can see two very different tectonic attempts at representing or constructing that surface. You see on the left, sort of contours of bricks covered in plaster to smoothen it out. On the right, you see individual sort of voussoirs. You can see the conical, the generators of the cone. Two very different ways of trying to represent this same type of geometry. I like looking at these two in parallel because you can almost see the struggle, like this really fun and amazing struggle to materially define something that is so specific and highly calibrated here. This type of surface was sort of became very well known through Robin Evans' studies of it and through a very specific version by Philibert Delorme of the trompe at Chateau Anet. And we learn about, in this case, the reason I mention it is because a very specific type of drawing technique had to be developed in order to be able to construct these types of geometries. So the sort of technological development to kind of understand how to build these kinds of geometries necessarily meant that a new type of drawing technique had to be developed as well. So there's this really beautiful one-to-one sort of overlap between the process of design and a drawing technique and then the geometry of the constructed form. So I'm interested in looking at that kind of translation. Like, you know, and this is actually this is so weird. I've always been so confused by this because this is a perfectly symmetrical trompe, But you see here that every one of these, not every one of them, but it's asymmetrical in its construction, and it gets me to think a little bit about that process of like the sequence of construction. It makes you think a little bit about the hand of the builder and the laborer. So how do we sort of translate something that is can be so purely and perfectly calibrated in a drawing? At the end of the day, this thing has to be constructed. It is not as simple as like, you know, producing a 3D print. And so thinking about how tectonics, in other words, the logic of assembly of material parts, oftentimes illustrated by the geometry of seams between parts, how can that sort of cue us into understanding that relationship between design and construction? I'm gonna go a little bit more quickly. I know we have a little bit of time, but I want to leave some time. But I want to basically show now a project, and it's sort of an ongoing long research project that kind of tries to address a couple of issues that I see in contemporary construction in that process of dealing with the relationship between design and building. So, you know, today we often see super complex curvilinear forms that are sort of post-rationalized with planar surfaces, kind of as like a texture mapped surface. Small, self-similar planar panels. Again, oftentimes we see this is like the only expression of tectonics that we see in these kinds of complex forms. The geometry of seams between these individual rectangular parts, but oftentimes they're not in concert with one another, nor does the part really sort of play a role in the generation of the geometry. It is just cladding. I'm interested in looking at how the material part and its DNA, in other words, like, you know, most of the material that we find, flat sheets, come in 4 foot by 8 foot dimensions. That is a direct result of the dimensions of a truck bed for transportation. And it's also dictated now a lot of other things about our tools for fabrication. So most standard CNC beds are 4 foot by 8 foot, et cetera, et cetera. And so there is this kind of DNA that is embedded or latent in the material that we use that I'm interested in seeing how we can sort of preserve that and have it inform some of the ways that we think about three-dimensional form. This is a house by the architect Eleanor Raymond, where she started experimenting with whole sheets of plywood when the wholesale plywood industry started supplying building materials in the late 1920s into the early 30s. But she basically uses entire sheets of 4 foot by 8 foot plywood as kind of proportioning device for the house. So in this case, she's kind of using the material in its most raw form as a sort of experimental venue. And she's really here trying to kind of reduce material waste. Like she's trying to use it in its entirety and also celebrate it, not kind of just have it be an afterthought. So like Raymond, I'm kind of interested in this, seeing how we can use rectangular sheets not to rationalize complex geometry, so not just to try to figure out how to build it, but instead to generate it. So I look here at a technique known as curved crease folding that is similar to origami. Origami, as many of you know, is a technique of paper folding that uses straight line creases and folds into planar surfaces. Curved creases or curved crease folding is similar to that, except instead of straight lines, it uses curved creases. And once you fold it, instead of planar surfaces, it produces curved surfaces. And these curved surfaces are developable. They're usually either cylinders or cones or other sort of developable surfaces within that family of geometries. So it's a very kind of useful technique to use when you're thinking of starting with the material part as the generator of form in this case. So this is a shade structure that I completed a few years ago in collaboration with the City of Cambridge, the Community Development Department, in addressing climate equity in the city. This was a temporary shade structure, very low budget and low cost. And the installation serves as part of a larger 10-year Resilient Cambridge plan that addresses the urgency of extreme heat. And so what in the city? And so we identified a few sites in the city that are urban heat islands. They experience higher average temperatures due to a deficit of tree canopy coverage. Part of their longer term plan is to plant more trees. But one of their shorter term ambitions was to introduce shade structures in the form of public art to under-resourced neighborhoods. And so this was the context of this project, given a very low budget, it's temporary. It became imperative to me that I develop construction methods that use, on the one hand, recyclable material, produce little to zero waste, and require limited skill and cost in assembly. So how could it be something that we could install quickly and not really need highly specialized labor that is expensive? So curve-crease folding was originally seen actually in the Bauhaus. This is also Joseph Albers, coincidentally, maybe not coincidentally. But in the Bauhaus, and he later took it to Black Mountain College, and then later picked up by David Huffman and Martin and Eric Demain at MIT as a way to create complex curvature out of planar material. The German structural engineer Heino Engel borrowed from ideas for folding for his experiments in surface active structures, which he referenced as the bending of cylinders. So there's a few aspects of this technique that I find really compelling. This is a subset of curved crease folding that I call sectional mirroring. And basically what it does is it takes any kind of developable surface, in this case just a simple cylinder, and then if you intersect it with a plane, trim it, and then mirror that section across that plane, join them together. If you unroll that surface, it will unroll back into a perfect rectangle. In other words, if you just crease it with a curve, this is a hyperbola, you can fold it into a cylinder that is bent. One thing I love about this is, like, if you think back to the TP example, it means that we can sort of design the three-dimensional reality entirely in 2D. There's a very specific relationship between conic sections in the flat state, so the hyperbola in the flat sheet, and the ellipse that is the intersection of the plane and the cylinder have a very specific relationship with each other. If the hyperbola, if you take the tangents at these points, is a 60-degree hyperbola, the plane that intersects it, or the bend in the cylinder, is also 60 degrees. So it means that you can design the entire thing in 2D and predict exactly what the 3D is going to be like. So there's a sort of economy of means here that I kind of love. I love it also just intellectually. I love the idea that you can sort of design in this space over here. It's like flat, 2D, and then there's this like inevitable 3D reality that emerges from it. You can aggregate it in 2D and it aggregates into 3D, like sort of working in two spaces at once. It also means that in the process of construction, there is, on the one hand, by the way, it also means that this is like a drawing that becomes a three-dimensional template too. So it's a drawing that is a model, almost literally. The curve is produced with a CNC bit, so it's almost just like the tip of a pen, but with a router bit. But it also means that the entire thing, in theory, could be stitched perfectly flat and then folded in place. I say in theory because in reality, there's other variables, there's weight, there's size, and things like this that make it cumbersome to do it. But there's at least a way for you to kind of develop a framework for the efficiency of flat to form, packing, transportation to the site, and then the process of construction, most of which can be done in 2D first and then inflated into 3D. The structure is composed out of 6 modules, all of which use the entirety of a 4-foot by 8-foot sheet of HDPE, high-density polyethylene, recyclable, cheap, and UV-resistant plastic. All of these sheets are basically just scored. None of them are cut, like no part of the sheet is cut and thrown out. The ones that are sort of half sheets are those who come from the same sheet. So the idea here, the primary constraint, was really to preserve the entirety of the rectangular sheet and see how much we can leverage that and its transformation into a 3D space. So here we are stitching 3 of the sheets together, flat, and then bending them in place as a kind of composite unit. Once they're folded, the timber frame is sort of erected separately, and then the sheets are inserted into the frame. One of the things that I was really interested in here also is kind of on the note of pictorial ambiguity, is how much we can also streamline the process of like limit the number of parts and produce difference from essentially sameness. So these three units are different units. All of them have the identical geometry in 2D, almost along the same hyperbolic curve. But depending on whether the curve is scored all the way, or scored or cut all the way, the three-dimensional outcome is drastically different. So from the same 2D template, you can produce three very different three-dimensional forms. This is kind of related to the drawing exercise that I showed earlier. The installation itself, the structure itself is rotationally symmetrical, which is another sort of like typological or spatial characteristic that is actually very useful for construction. So, you know, you design or build one side and then you're like, okay, now let's just do exactly the same thing on the other side. But because of things, you know, objects placement in three-dimensional space and on sites, there's like, it doesn't actually look like it repeats. It looks like it is idiosyncratic on either side. I'll wrap up in a minute, but I'll show basically some of the developments from there and maybe address some of the shortcomings of this. One of the things that I kind of like about this is that there's, as a process, and that kind of keeps me going, it feels kind of limited to think of, you know, using this rectangular, like how many times can you do this and produce difference, or like feel like you're innovating or doing something new. One of the things that I kind of like about this is that you are also trying to kind of invent new types. Like in this case, the sheet itself can form, on the one hand, kind of conform to like a very kind of vernacular cable outline because of the straight line edges of the cylinder, but then also kind of produce this undulating, periodic, sort of hybrid barrel vault surface on the interior. There's something kind of, I think, interesting to me typologically about trying to think about those things, things as well. The walls fold down to become seats. The shade structure was introduced in a part that has a high footfall. It serves many different types of people and communities in the area. So it's kind of really nice actually to see how different people use it. Daycare center, kids from the elementary school nearby who don't have their own recess space, public housing residents across the street. There's something kind of nice also about, in this case, even though this seems like a very complex, maybe sophisticated process, it's actually really, really simple. And it becomes kind of accessible and really easy to describe it to anybody. So we did this event around Earth Day in 2022. Volunteer group in the area wanted to host local school children and have them think about sustainability in building and urban heat islands and things like this. And so we demonstrated to them how this process, just using paper folding, but also like one of the seats, how you can use very simple materials to produce something that is structural. Sort of thinking forward from here, again, kind of the larger picture of this type of work also is the scalability of it, but also the versatility of it too. So temporary structure is going to come down. How can we maybe reuse the surfaces and not throw them out? So we sort of created these plywood frames to recreate benches that could be dispersed in public parks. Just to show a few kind of developments in the process here. So I've been working on this for a few years now and kind of developing the vocabulary of the types of forms it can produce. There were lots of problems. I call it a sort of like, you know, close to zero waste. It's a very wasteful structure that we can talk about, but it's also not super efficient in other ways. Like there's efficiencies in maybe the process of 2D to 3D and this kind of thing, but it required a lot of external structural members and other stuff that basically meant that the surface itself couldn't really hold a lot of responsibility. And so one of the things that I've been working on now is expanding the repertoire of vocabularies where moving away from the sort of linear accordion type that really wants to bend back out. So structurally, it's really precarious. I'm thinking about ways of getting the surface to become a little bit more structurally responsible. So having it turn a corner, having it self-intersect. So these studies here basically show radial versions of it where an external frame is not needed. It still has distortion problems. Working with engineers also to think about different scales and materials that we can use. Thinking about labor and who these kinds of structures are for, really. I mean, thinking about maybe the applicability of this. Maybe this could become deployable disaster relief shelters. Maybe it happens at a much larger scale and they are permanent and more expensive. It could straddle both these kinds of worlds, but thinking about other ways of streamlining where, you know, can you make it almost like build in as much geometric intelligence into the part so that even stitching sheets with one another doesn't require mechanical fasteners and things like this? Can the geometry of seams be built into the process of fabrication? I saw very similar forms of like this upstairs on the 3rd floor, but also thinking about other types of geometries here. I'm using the rectangular sheet to produce spherical surfaces, which actually become super structural just inherently. Larger scale cantilevered structures. This is sort of just a sampler. And lastly, this is a proposal for an indoor installation that tries to test like I'm testing for the first time a sort of like fully enclosed radial circular structure out of bent plywood. It's a structure that is somewhere in between like a room and furniture. This is entirely a result of the 4 foot by 8 foot again. So it sort of has this kind of, in the process of transforming from the flat to form, has very limited, has a very specific relationship with the scale of the human body that I'm kind of interested in. And I think I'll end here. I know I went a little bit over there. Okay.
Thank you so much. I hope that you will find it a super inspirational lecture on the power of knowing. It's most simplest, probably. Are there any questions?
Not all at once.
Okay, yes.
So at the beginning of the lecture and kind of before, you were talking about how sort of people and craftsmen have used their materiality to then establish these shapes, and it's part of their work process that gets us there. And then I think it's rather interesting that you are now almost, I don't want to be like screwing, but it almost seems like you're taking the craftsperson out of that process, and it's like very prefab, plasticky, and I guess that's maybe sort of your intention, but I'm kind of wondering, what are the broader implications of taking the craftsperson out of that and ignoring that work that they might be doing to then just have these pure geometric forms produced by the architect?
Excellent question. And is like really, I'm like so preoccupied by it, by the way, like, because and we often talk about, it's a complicated question because, you know, I mentioned when I described the context of the shade structure, for instance, where I would love to work with contractors as a designer and think about ways that we can like, you know, fuse our languages and our processes with each other, maybe also learn from each other in the same way that like a musical performer will like really kind of like, you know, if the composer is alive, like wants to work with the composer. And we don't really have that in architecture. Like we work with contractors and we work with craftsmen, but it's almost always like, you know, the contractor is not celebrated in the same way that like a pianist is, right? And when you look at the context of something like the shade structure where labor is so expensive and the client basically literally had $5,000 and they said, how can we do something without the need to hire contractors? You know, there ends up being a sort of venue for this work where you do have to bypass skilled labor. And it is awful on the one hand, because yes, it means that, you know, is this the ideal of what I think the world of like building practice should be? Absolutely not. I think skilled labor is essential to our practice. And I would want to incorporate a little bit more. But there are venues where I think like considering how, on the one hand, there's a sort of like flip side, like narrative to this maybe where with structures like this, a big part of the research was also to think about even members of the community becoming their own builders. So if we're sort of bypassing skilled labor as a way to get something out to a community more quickly and more cheaply, there is also something really nice about having people feel empowered by the ability to build their own, environments too. So, it's a complicated question because there's a good side to it. There's also like a not so great side to it. But it's an ongoing question. I love that you asked that because it's super important.
In the beginning of the lecture, you were talking about or the difference between creating these curved structures as just a skin and the interior program having no relation to the outside curve, and how in earlier times like TPs or other curved structures are used just very functionally, and so your concert hall was sort of moving in that direction. Do you have an opinion on certain programs that might fit this movement towards functionality better than other programs might? So the concert hall itself, like the seats now all become pretty much equal, and so there is no bad or good seat. And so is there a scenario where that isn't what you want instead?
I think I understand your question. Are you saying that is the technique better used or better applied to specific types of buildings or programs versus others?
Yeah, pretty much.
Or, okay, maybe I'll address my interpretation of your question. One is, there's always going to be good and bad seats. It's like impossible to create space that's like, I don't want to say it's not pure. It's like, you need bad spaces, like you need dark spaces in buildings, you need like crochet, you need things that are like not great. You need a hierarchy of spaces because buildings need a variety of, different uses of spaces and qualities. In an ideal world where like ticket prices are not a big deal, it's actually also good to have good and bad seats because you can pay less for a worse seat and still be able to see the show. So the seats in the theater are actually not designed to be perfect. Like they don't provide a perfect viewpoint for all audience members. But what they do is they provide an experience that is equal for every audience member upon entry into the theater. So it's a different kind of like preference for experience. It's less so like your experience while watching the performance, like what you're there to do. It's more so about making you a little bit more aware of who you are in the building as you move through it. And then it makes your relationship to the performer also a little bit different. The fact that you enter the auditorium in the center where the performers usually are, there's usually a big separation between audience and performer, and this sort of brings you a little bit closer. So like, it's similar to the kind of the conformal mapping example that I gave, like there's goods and bads. There's like, to give up one good variable means that you're also preferencing something else. And I think generally maybe that's like a useful way of thinking about space. I don't think there's like a optimal type of building, maybe, if that's what your question was also, like if there's an optimal building for this, I don't know. I think like the theater is interesting just because it already has that kind of like complex history with personal points of view and things like that.
We had one more question.
You were talking about earlier about how you created that the cradle, the grid, the illusionary cradle that turned into a grid when you projected it for your master species. How did you first come up with that idea? Like, are you interested in creating something like that?
I actually, my very honest answer to that is I didn't actually approach this technique from like a perspectival lens, unintended. Like I actually started looking, I was really interested in the relationship in inversive geometry. And I was interested in the relationship between spherical space and Cartesian space. I kind of accidentally actually discovered the perspectival thing with my model. So I had made a model, and then I was also modeling things digitally. This is kind of going counter to what I was just talking about, but I was modeling things in 3D in Rhino. I happened to snap the view in like this very particular place. And I almost didn't believe what I was seeing because the image that I saw on the screen was not what I was modeling. And it flattened into that perfect thing. And I was like, oh my God, that's like not what I was trying to do, but like, that's really interesting. So that's kind of how I landed on that. And because this technique has never been used in that way. Like it has always only been used as a indexical tool to project, like to map the sphere onto a plane. It was never really considered as like something that could be, you know, spatial. So I was exploring something else entirely actually with that technique, and I kind of discovered it, and it became an obsession. And I feel like there's actually something kind of great about that. Like, it's nice to not know what you're, or it's nice to maybe have some goal or ambition of like, you know, the things that you guys are working on. Let yourself discover something and let go of something else that you thought was like interesting. But like what I stumbled upon kind of by accident is so much more interesting than I was trying to do. And I can call it interesting, by the way, because it's not a technique I invented. I kind of just found it. I like discovered it, but I discovered it in a way that maybe like no one else had used it. So it became super, super exciting for me to kind of dive deeper into it. But that's my very honest answer to you. I don't think I've ever really said that out loud to anybody.
Thank you.
This is relative to speed first.
Yeah.
Yes, I would love to like have way more questions because I think this question session is at least as interesting as the presentation itself was. But we are running out of time. So I say one last question. Okay. That you are close to the fire, okay? So I let Parnas go.
Hi, I'm Karina. I had a question. It was a really nice lecture, and I did like the connection of your idea to the perception and psychology of Gestalt, and it was really interesting for me that perspective. What do you see the next step for connection that you make in the perception, and yeah, exactly what after gonna be, after it's gonna be?
That's a good question. That's like my therapy question. I don't know. I'm like figuring it out, you know? But I am actually interested in, they seem like kind of two separate endeavors, you know, like the perceptual and the material, but like if I maybe hopefully try to make an attempt at how they're related, at least in the way of thinking, I don't know if I'm trying to relate them so literally to one another, you know? But for instance, I am interested in, like, the reason the perspectival tool is so interesting to me is because it does have an immediate, it has immediate consequences on form. Like, it can almost invent new types of surfaces even, if that's the way that you're kind of thinking about things. And so eventually there is a material reality to it that could become really interesting and useful. Like, one of the things that I tried to do actually with the spherical one is, you know, it's all of my representation of it is represented very sort of like mathematically, you know, like grid. But I tried to make images of like, you know, what if this were like a running pond of brick or something like this? Would I see, like, when it's flattened, do I see it? Like, can I sort of like replicate the realities of like material construction, and how would it either, like, how would the perception still hold or maybe break? I don't know. But I'm interested in also just thinking beyond, like, beyond the visual. So I mentioned this a little bit, like I'm interested in maybe how the haptic can begin to sort of like cross over that boundary between the visual and then other forms of cognitive and bodily awareness of things. So it's a little bit less literal, and it's less about like, okay, like these things are so linearly connected to one another, but they begin to sort of inform each other, I think, for me, like in my own. Maybe I'll find a third, I don't know, like it would be great for me to find something totally new. I don't know, but to be continued, I don't know.
Thank you.
Thank you so much again.